Hi everyone, we're going to continue to talk about the chain rule. And in this lesson, you'll see that I'll put the chain rule together with the product rule, the quotient rule, maybe a chain rule will happen, along with e, ln, and b to the x. So we want to see when to do what. So you're going to look at a function, decide what's really going to push it, and then what kind of follows down, like that chain link after it. We'll start with f of x is e to the 4x plus 9 to the 5x to the power 6. The power 6 is the pusher. It's the one that's most important. So when I go to take the derivative, I'm going to start with f prime of x. I'll bring the 6 down. So first time through, I leave e to the 4x plus 9 to the 5x. And I change that power to a 5. So first I'm dealing with the power rule. So power comes down, it reduces by 1. Then I go back inside and do the derivatives. I look at e to the 4x. I write e to the 4x, but I need to remember to multiply by the derivative of 4x, which is 4. And then I'll add 9 to the 5x. The derivative of 5x is 5. And then I need the natural log of the base, which was 9. As big and messy as this is, we're done. The only thing I could see you doing is maybe bringing the 4 in front of the e to the 4x, but it's not necessary. You can leave it exactly like it is right now. We said the chain rule would have a lot of pieces, and you can see here's a bunch of pieces to our answer. Our next problem says the square root of the natural log of x. We want to make sure we recognize the square root as a power. Let's try rewriting this as the natural log of x raised to the 1/2 power. Now when I take the derivative, this is the chain rule. The power comes down, it's 1/2. I keep the natural log of x. Now I change the power. Remember, I'm subtracting 1, I get negative 1/2. Now I go inside. The derivative of the natural log of x is 1 over x. I'm okay with this. This looks fine, but you might see it written other ways, so it's important to see how else we could write this. I really have 3 fractions, 1 over 2. The natural log of x to the negative 1/2, the negative tells me the natural log is really in the denominator, and I have 1 over x. So if you start gathering what goes in the denominator, the 2 goes, this x goes, and then the natural log of x to the negative 1/2 would be the square root of the natural log of x. The numerators in each case were 1, so here's my derivative is 1 over 2x square root of the natural log of x. Number 3, I have h of x is 5x cubed times e to the 4x minus 2. Remember how I said you really need to pay attention to how you would say this. And what did I say? I said it's 5x cubed times. That times immediately says we need to do the product rule. So I take the derivative. I'm going to start with the 5x cubed. The derivative is 15x squared. I don't do anything to the e to the 4x minus 2 the first time through. Remember, I do f prime g plus g prime f. So let's go back through. So I had 15x squared e to the 4x minus 2. I'll go back to 5x cubed. E to the 4x minus 2 will be e to the 4x minus 2, but this time I need the derivative of 4x minus 2, which is 4. You could put the 5 with the 4. That's about the only simplification that could happen. So that says 15x squared e to the 4x minus 2 plus 5 times 4 is 20 x cubed e to the 4x minus 2. You might notice also that there's an e to the 4x minus 2 in both parts. There's x and there's x. There's 15 and there's 20. 15 and 20 have 5 in common. I could factor it out. X squared and x cubed have x squared in common. It could come out. E to the 4x minus 2 is the same in both terms, so I could take that out. So if you're looking to practice the factoring, it's a good time to mess with it and try to see how familiar you are with the steps. 15 divided by 5 is 3. The x squared is already taken out. The e is taken out. Plus 20 divided by 5 is 4. X cubed divided by x squared is x. So here's another way to write this same function. Number 4 says f of x is 12 over 7 to the x minus 5 to the 4th. Now this is one you want to look at and decide, should I do the quotient rule or not? And I'm going to say it's not. How do I decide? I decide because the numerator is a constant. It's only 12. That means I could go ahead and rewrite this as 12 times 7 to the x minus 5 to the negative 4. So when I have just a constant as the numerator, I can rewrite it as a power and then just use the chain rule. Now I take the derivative f prime of x. The negative 4 comes down. Negative 4 times 12 is negative 48. I leave 7 to the x minus 5, but I drop the power. Negative 4 minus 1 is negative 5. Inside, I go back in, I have 7 to the x, which would be 7 to the x, natural log of 7, and then the negative 5 is a constant, so the derivative is 0. You could leave it like this, that would be fine with me. If you wanted to rewrite it, I would leave the negative 48, the 7 to the x, natural log of 7, I would put those two together, they're being multiplied. The negative 5 says you would drop the 7 to the x minus 5 to the denominator and make it to the 5th power. Let's try an application. The total cost of making x electric bikes can be modeled by the function c of x is 12 plus the square root of 3x minus 5, where c of x is in thousands and x is greater than or equal to 2 and less than or equal to 150. I graphed the function so we can see how the cost function is changing. So what we want to look at is really how is the cost function changing? How do we see the increase or decrease happening over time compared to how many bikes are being made? To start with, we just need to find the marginal cost. I'm going to rewrite c of x as 12 plus 3x minus 5 to the 1/2 power. That way I can use the power rule to find the derivative. And really we're using the generalized power rule because I have this quantity 3x minus 5. When I take the derivative, the 12 is a constant, it goes away, the 1/2 comes down, I have 3x minus 5. Now to the negative 1/2 power, inside the 3x minus 5 becomes a 3. c prime of x is equal to 3 times a half is 3/2, 3x minus 5 to the negative 1/2. Now that we have the marginal cost function, I want to evaluate it at a couple of numbers. We're going to find c prime of 58 and c prime of 135. But the easiest way to do that would be to put it in our calculator. So I'm going to pull up Desmos, and I'm going to put the derivative in Desmos. I'm still going to call it c of x, but I'll use lowercase c maybe so that we don't get confused between the two. And I'm putting in 3/2, 3x minus 5 to the negative 1/2. I want Desmos to evaluate c of 58 and also c of 135. c of 58 says 0.11538, and then c of 135 says 0.075. If we look at the graph of c of x, we can see it's always increasing. But the way it increases is not constant. When we put in 58, we got a value of 0.11538. When we put in 135, we got a value of 0.075. So what we can tell is that the value is getting smaller as we make more and more of the bikes. So what we need to decide is what we call this increasing at an increasing rate or increasing at a decreasing rate. Because the increases are getting smaller, we want to call that increasing at a decreasing rate. Our last one says Athena drinks a large cup of coffee containing 250 milligrams of caffeine. The amount of caffeine that remains in her body t hours after she drank the coffee can be modeled by the function c of t is 250 e to the negative 0.173 t. We are going to first find the rate at which the caffeine in her body is decreasing after 1 hour, and then we're also going to find the rate at which it's decreasing after 5 hours. Let's start with 1 hour. We need to calculate the derivative. I have 250 e to the negative 0.173 t, and then the chain rule tells me to multiply by negative 0.173. If you wanted to, you can multiply 250 by negative 0.173, but I'm just going to go ahead and put this whole thing in my calculator at once. C prime of 1 would be 250 e to the negative 0.173 times 1 times negative 0.173. C prime of 1 is negative 36.38 milligrams. So the amount of coffee that's leaving the body between hour 1 and hour 2 would be 36.38 milligrams. Let's look at what happens after 5 hours. After 5 hours, I have C prime of 5 is 250 e to the negative 0.173 times 5 times negative 0.173. So after 5 hours, the decrease is negative 18.21 milligrams. We're losing more caffeine at the beginning, when the caffeine level is the highest, and then throughout the day, the amount of caffeine that you're losing is decreasing because there's not as much left.